Hello everyone, and welcome back to another GIS statistics lecture video. And in the final video of this series, I want to talk about something called normality. And I want to talk about normality for two reasons. One, it ties together pretty much everything we've talked about up to this point, all of the sort of descriptive statistics, mean, median, standard deviation, hypothesis testing, and p-values. It also ties in the graphing concepts that we've covered, but also normality in particular is an extremely important concept in inferential statistics going forward, because a lot of the time when we're approaching things like regression, which is what we're going to spend the later half of this semester talking about, one of the critical underlying assumptions is that our data is what's called normally distributed. And we'll check normally distributed by checking normality. And well, it's not necessarily imperative that the data be normal. At the very least, you have to at least have made a good faith effort to show that you know whether or not the data is normal. So again, we're talking about normality. And what normality is asking basically the question of, does the data come from a normal or on here I'm going to put Gaussian distribution? All right, so what does a normal distribution or a Gaussian distribution mean? Well, what that means is if you have a graph like this, right, here's going to be the values, and here's going to be the frequencies, right? The idea here is that, and we're going to have the middle of the values, right, this, all right, actually let's make this a different color, all right. This dashed red line is going to be the mean of the data set, right? A normal distribution is going to look something like that. Now, why do we care about a normal distribution? Well, a normal distribution means a couple of things. One, it means that extreme values are relatively rare, and that most of the values are going to be coming from the sort of moderate or middle values, and that this whole thing is going to be centered around the mean. So if you remember back to when we discussed the mean, I said that the mean is generally a good approximation of the center of the data set, and that you can sort of expect most of the values to be close to the mean. We were sort of in that discussion, we were sort of assuming that the data was normally distributed, right? We were sort of assuming that the distribution of observations looks something like this, where most of the values were in the middle, and you had the frequency of extreme values was relatively rare. And again, sort of the underlying assumption of a lot of inferential statistics is that our samples actually do follow this distribution, right? Where the majority of the values are sort of in the middle, and that the extreme values are sort of rare. Right? So this is sort of the gold standard of what we're looking for. We're looking for this normality. So how do we sort of know whether or not this is true, right? How do we sort of expect or determine whether or not our data comes from this normal distribution? And there's 4 ways, and we're going to go through each one. Right? The first way is to compare the mean and the median. Right? Compare the mean and the median. If they are close in value, data is more likely normally distributed. More likely normally distributed. Right. If they differ, in value, data is likely not normally distributed. Now, I will say this before we go any farther, is a general rule when you're first looking at a data set or first looking at a variable, you're going to want to do all of these things, right? You're not just going to want to do one, you're going to want to do all four of these, right? You're going to want to compare the mean to the median. That's going to give you an indication. Then the next thing that you're going to want to do is you're going to want to look at histograms. Right, so the second thing you're going to want to do is look, that's a terrible K. You're going to want to look at histograms. Right. And the reason you want to look at a histogram is because a histogram, right? A histogram, by its very definition, right, plots the value along the x-axis against the frequency along the y-axis. And if we scroll back up for a second, right, you'll see that when I was talking about the normal distribution, right, I literally made a graph that showed the values on the x-axis and the frequency on the y-axis. And we said that we were sort of looking for this bell-shaped curve where the vast majority of the values occurred in the middle. Right? So I literally just described essentially a histogram. So if we look at the histogram of the data, right, we can look for that bell-shaped curve. And if we see the bell-shaped curve, that is a good indication that the data is normally distributed. Right, so I sort of cheated here, and these are pre-generated data sets that I knew were and were not normally distributed. Right, and so if you look here, right, you'll see we have what is basically a nice bell-shaped curve. Right, if we look over here, right, we do not have a nice bell-shaped curve. In fact, instead, we have this sort of table looking. We have this sort of table look, right? Where pretty much all of the values have an equal frequency. Right? This is called a uniform distribution. Right? In this case, right, we see many of the values have sort of middle, moderate values, and our extreme values are rarer. Right? This is exactly like the type of shape that we're looking for in a histogram. This is sort of the opposite. This is almost the worst case scenario. This would not indicate normal distribution, right? So when you look at the histograms, right, you look for a bell-shaped curve with the majority of values in the center. And when I say majority of values, what I mean is the highest frequency. Right, because you could imagine a scenario, and I'm going to do this in blue, where you have something that looks like this. Right. This would not be normally distributed because the majority of the values are actually not in the center of the graph. Right? The highest frequencies at the low end, not in the middle. So this blue graph would not be normally distributed, even though it kind of has a bell shape. Right? It's a bell shape, but there's a long tail. So this is not normally distributed. Right? This red one is because the center of the graph, right, the majority of values is in the center, not off to one side. The third thing you're going to want to do is you're going to want to look at what is called the QQ plot. Right. So what a QQ plot is a QQ plot is essentially a graph of the quantiles, right? So the data are converted to quantiles, which we've talked about quantiles, right? The data is converted to quantiles, and then you have your sample quantiles. So these are the things that you actually measured along the y-axis. And then on the x-axis, these are the theoretical quantiles. So these are the quantiles that are calculated assuming whatever distribution you're looking at. So in this case, we're talking about a normal distribution, right? So I'm going to use red here. I'm going to make it a little thicker. Right, so each one of these dots, actually let's do the dots in green, right? Each one of these dots represents a data point in your data set, right? And this black line here, this solid line, this line right here, this is what you would hope to see assuming your data is normally distributed. Right? This solid line here, this is a perfectly normally distributed data set. And so what you would hope to see is that all of the points are either on or very close to that line. Right? So in this one, right, this is a normally distributed data set, and you can see that because almost all of the points lie directly on or very close to the line. Right here, right, this line means this line here, this is the same thing. Right? This line right here, this solid line here, right, this is the perfect normality. Right? This is where you would want all of your points to lie along the line. But what you can see happen here, right, is we have all of these points over here and all of these points up here that start to very strongly veer away from the line, this normality line. So when you see something like this where you have points veering strongly away from this line, that is again a strong indication of non-normality, right? So this indicates normal, right? Indicates normality. This indicates non-normality. Okay, so hopefully that makes sense. And we're gonna go through some examples in R of how you would actually generate these things. But the final thing that you want to look for, right? The final thing that you want to do is once you're fairly confident, that your data has an issue, is you want to run a test statistic. And the one that I would probably say 9 times out of 10 you're going to want to run is called the Shapiro-Wilks test. Right, and the test statistic in this case is a W. Right, and when we talked about hypothesis testing and p-values, right, what we said here was that you have to know what test you're running, right, the Shapiro-Wilks test, what your test statistic is, which is W, and W again is an indicator of normality. And then the most important thing you need to know are what the null hypothesis and the alternative hypothesis are. Right, so what is our null hypothesis? Right, the null hypothesis for the Shapiro-Wilks test is that the data comes from a population with a normal distribution, which means that the alternative hypothesis, right, is that the data comes from a population that is not normally distributed. Right? So in this case, right, we actually want the null hypothesis we actually do not want to reject the null hypothesis, right? So assuming that our alpha value is 0.05, which is again sort of the standard, right? So if it's greater than 0.05, if it's greater, right, if p is greater than 0.05, right, we do not reject the null hypothesis. Which means we move forward under the assumption that the data comes from a normal distribution. Right, if the p-value is less than or equal to 0.05, right, we do reject the null hypothesis. Right, which means that we do not feel comfortable in saying that we would get this data assuming that the population has a normal distribution. Right, so greater than 0.05 indicates that we are kind of assuming the data is normal. Right, we feel confident that we got this sample given that the population has a normal distribution. If the p-value is less than 0.05, we basically are saying that we do not feel comfortable saying that we got this data assuming that the population has a normal distribution. So hopefully that made sense. I know there's a lot here. Just to kind of quickly recap, right, we're trying to figure out if the data is normally distributed. The first thing you want to do is compare the mean to the median. If they're similar in value, you're probably normal. If they're vastly different, you're probably not normal. You're going to look at the histogram to kind of see what kind of shape it has. You're going to look at a QQ plot to see how the points fall along that expected normal line. And then you're finally going to run a test, most likely the Shapiro-Wilks. And the idea is that you want the p-value to be greater than 0.05 because you do not want to reject the null hypothesis. So hopefully that made sense. Again, if any of this was confusing, I encourage you to pause the video, go back, rewatch the parts you're confused about. And as always, please reach out. Thank you.